Hello, my name is Stephen Burns. I'm a geophysicist with Geometrics, and today we're going to learn how to process atom seismograph data that has a higher mode present in the data. We're going to learn how to fix this. Now, before we launch into the data analysis, let's review what a higher mode is. Any wave phenomenon always consists of a fundamental tone and overtones, or in other terms, a fundamental mode and higher modes. Seismic surface waves also consist of a fundamental mode and higher modes. Most surface wave dispersion curves mainly consist of the fundamental mode, and analysis usually only needs to treat the fundamental mode. The higher modes may, however, dominate in several types of velocity structures, such as a model in which a high velocity layer overlays on a low velocity layer, or a model in which a high velocity layer is embedded in low velocity layers. Surface wave analysis needs to take into account the higher mode for dispersion curves attained at such complex velocity models. Okay, let's begin processing the data. So we're going to open up that data set. And we're just going to open up the folder that's in, which is higher mode example data. Okay, we have 18 atoms, 18 seismographs, one common time block. The common time block is when all the atoms are on at the same time. And here we can see our data. And if we go up on the arrow keys, it increases the gain. If you go down, it decreases. And at the bottom here is our atom 3C. So we did have a 3C atom that was recording, and we're going to select the vertical component from this data for this example. So now our common time block has already been selected. So we would want to go to CTB up here, common time block. We'll click that. And it says there's a different number of components mixed. You want to select a single component. Yes. Vertical. Okay. No bandpass filter. Here's our data. And you can see that it looks just the same as it did before. Now, if you wanted to snip it, as shown in our earlier processing videos, you just go left with the arrow key to move that yellow gate, or if you hit tab, you move the gate to the right side, and then again, you can use your arrow keys. But we're not snipping anything here, so we're just going to go straight to SPAC. So we'll click the SPAC button here, the next step of the processing. And it's going to ask us for our geometry. And I already have an array file created for this, which is a simple text file. And to get that, we go to our folder here, and we'll open up the higher mode array file. So now we have our manual array. Hit OK. This is going through how many time blocks there are, the number of pairs, the number of spacings. Hit OK. And this is our data. So looks good, looks very good. Great coherencies across from all the way from 0.1 to 10 hertz, and a good distribution of pairings and spacings. So we have, it's like every meter or so we're getting a different spacing, which is really good. And here we see that's really nice and clean. And this is only 0.2 meters different, but looks very, very similar. So good data. Now, if we wanted to remove some of the extraneous data from this set, the way you could do that is you could increase the data gain, which I just did by using the up arrow, and we can maybe remove some of these, vertical bands. So if we go there, we click on this time block. This is 1 minute time blocks, each one, and each of these colors corresponds to one of the traces up here. So basically, you look at the coherencies within the data between the different geophones, and you look at them with each minute. So some of the minutes have where data was collected, the coherencies are less. Some of them have really, really good coherency. And then you take that average. The black line here is your average. The red line is the one that you've selected. So if I click this yellow, you'll see the red line shifted. And if I click the blue line, right, etc. So I would say, we could remove that guy if we wanted to, and we could remove this minute near the end of the survey, and maybe remove this one right here. I like to process my data as background noise as possible. I don't like it when there's obvious noise throughout. This data could have been caused by like a car driving by, for example, but there's a lot of reasons. So I don't want to pull too much out though, because it's nice to process with more time. And the way this processes is it takes the average. So this little blip right here only comprises maybe 20 seconds, and across a full 30-minute sweep, its effect on the data is very minimal. But these ones are a little broader, they're a little stronger, so let's remove them. So we still have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 2, 3, 4, 5, 6, and like 6.5. So we still got 26.5 minutes of data, so that's good. But we're going to soon see what I mean when it comes to the higher mode. This data has a higher mode that pops up. So to see that, we're going to go to phase velocity right here. And we'll click the PV button. And we'll go with maximum of 30 hertz. This data was collected with 2 hertz phones, and beyond 30 hertz or so, you're not often going to get good data, good coherency beyond 30 hertz with a 2 hertz geophone. But now we have our coherencies on the left and our phase velocity dispersion curve on the right, and we can really obviously see this higher mode, right? So we have our data comes to a point here. This is a very fast velocity, and then, it's some of the fastest of the data set, right, if you look at the actual data, but here the higher mode is much faster. And this is a low frequency. And then you can see it kind of forms a shelf here and then goes down again. But this jumps up. And if we move our minimum, we can see it a little better. Right? Here is what it looks like. And you can see that this is kind of all got shifted up and it jumped to that higher mode. Now, if we were to just drag our cursor down to the bottom, which is right about here, I'd say the data probably stops around 25, and this is about the bottom of it. So we drag the cursor there, and it auto picks based off of the best fit, and we see it jumps up to this higher mode. It's not what we want. You don't want to process that. So how do you fix that? Well, I like to take a photo or a snapshot of this raw dispersion curve, and we'll get that. And then I like to layer that alongside when I'm creating my pick, so I can make sure these picks are really accurate. So we'll do that, and then we'll type in snip for the snipping tool, and here it is alongside. And if I lower this again, now it jumps up. It gets a little hard to see in here because of all these red dots, right? But it's a little easier to see when you have the actual data. So what we're going to do is we're going to draw lines, best fit lines via our best judgment through this data here, and then it's already well picked in this zone here. So we're going to connect these two. And the way you do that is you left click and then you draw a line to the right, and that'll create a straight line for you. If you left click here and draw it up, it'll draw an angle. If you click there, draw it down, it'll draw an angle. If you go the other direction, it behaves differently. So let's go, and first off, let's get this part established here. So I'm going to click. I don't want this to be this kind of goes up a little bit, which means there's a little bit of a low velocity zone here for whatever reason, though this data is really well confined, so I don't really want to touch it. But you can see how this kind of got blown up a bit because of the higher modes. It's probably not actually that elevated compared to the 5 to 10 hertz data, so I'm going to probably take it from about here and get this line first started. So I'm going to left click and drag, and we can clean this up as we go too. to make it look nice. And you can just keep doing that. And we're just going to follow this best fit. And now we're about to connect them. You can see that the dots automatically came down from the top, except for a few of them. That's fine. And I'm also going to clean up a little bit over here. Just get rid of some of these dips. I think it's a little too much. And then also that little high peak right there. But we can see this fits really nicely, right? And then I'm also going to, this little spiral pattern, I'm going to clean that up a bit. And when I do this, I like to save my picks so I can see them later. It helps, you know, because you come back to this data a week from now or a month or a year or whatever, you can see what you did. Though, of course, the data is still going to be the same. So now we have our data, and I'd say that it looks quite nice. You can see it goes right through this band here, straight down. Higher mode has been ignored, and this is probably more what the actual site looks like. You have the zone from about 5 to 20 hertz or so, where it's around 300 meters per second for the phase velocity. And then it kind of levels off a little bit lower there. And then beyond 25 hertz, you know, I think there's just too much noise there to accurately pick it. But at this point, we can go to our dispersion curve button here. So the red line with the black X and Y axes. And we'll click that. And that will launch Wavy Queue, which is another SeisImager surface wave module, software module. So we'll click that. It says, do you want to interpolate to reduce data? I like to interpolate to about 300 because if you don't interpolate down, it can take a long time to invert your data, to undergo inversion. So I like to interpolate to 300, but you can make that whatever number you want, right? You can make it 100 if you want. Though, of course, the more points you take out, the more the quality of the data is reduced. 300 is a nice number. Hit OK, and now we are in Wavy Queue, and I'm just going to bring in our graph right there, and we can see here on the left, and I like to also have the SeisImager SPAC software module. I like to keep that there on the right so I can see it as I play with these dots. So the first thing I'm going to do is I'm going to remove this data right here. And I'm going to also then cut off this data, and I'm going to cut off the data to the left. But first, I'm going to remove these points, which are just bogus. So the way I did that is I clicked up here, the arrow with the red square. The icons are really small on my computer because I have a 4K screen, but it is an arrow with a red square, and that lets you drag and to like select a box, and then it will highlight them red, and then you can delete them. If you highlight too much, and you don't know how to get out of that, just click the regular arrow. And then that'll just reset everything. So again, I'm going to select this guy right there, delete that, and maybe even select this one. Hit delete. Looks good. Now I'm going to go to Dispersion Curve, and I'm going to delete the picks outside of the gates. So I now have a red and a green gate. And arrow keys will move the gates, and you use enter to move from the first gate to the next. But once you've hit enter twice, it will cut the data. And you can't just Control Z or go back to get the data. You're going to have to go back to SPAC, this section of the screen, and then hit the dispersion curve button again. So make sure you pick that data well. And usually a good place to pick that is at the highest velocity point. It depends because you can see here this forms a little bit of a shelf, and clicking, selecting from here will get you data at a greater depth because it's lower in frequency. But this small movement here from like 1 to 1.5 hertz will create a very large low velocity zone in your data. So if you wanted to, if you were confident with your interpretation that data was, the geology was that stiffness of like 450 for the meters per second, the shear wave, then you could always level that peak off. But in this case, I think it's splitting hairs, and I just like to go with the highest point, and that will, it's probably the most accurate usually. So we'll hit enter there, and then for the right side of it, it's right next to 25. I would say it's actually a little bit to the left, maybe like 24.5 hertz. So I like that right there. I'm going to hit enter. You can see the data disappeared. So there it is. And if we wanted to, we could smooth out the curves, but we really don't need to, because the theoretical dispersion curve will fit that quite nicely, and smoothing this won't really make any difference. It might make a difference here. It might bring these values up a bit as it just kind of averages them out a little bit more. So, but ultimately it doesn't really matter. So we'll click VR to show the parent velocity model. We'll get our depth, and we might have data a little bit deeper. Let's go to view to change the axes, and let's just change that to like 150. And it looks like that was the deepest data point, which is 112 or so. So we'll go back, and we'll go to 120 again, and we'll make our maximum velocity 600. Okay, so here is our parent velocity model. We can see that we do have a little bit of that low velocity zone there, but that's what it came back in. If you look to the right, this looks very clear. So I don't like to mess with data too much, even if it shows me things that geologically might be not the most common. So these things, low velocity zones, do exist. So if we want to create now our model and do the inversions, we have to get a theoretical dispersion curve. We have to create an initial model. So we have our depth here, 100 to 10. We'll go to velocity model. Actually, we'll go to MASW/MAM 1D. We'll create our initial model. Here you can choose your number of layers. You can choose your depth. There's an advanced menu. We won't deal with that today. The purpose of this video is to show how you can select, you could deselect that higher mode. So now we're just processing to show you the final result. So this all looks good. We're going to hit OK. Here's our initial model. If we go back to DISP1 or display 1 or dispersion curve 1, then it'll show that dispersion curve. Hit the red star to calculate your theoretical. And that'll take just a moment. There it is. Our RMSE error is about 25 meters per second, so very good. It's a very good error to have. And now we can go back here, and we can hit inversion LSM, which, if you look there, is velocity of the shear wave and also thickness. And the default is 5 iterations. I found that typically 5 inversions via the least squares method is all you need, especially if you set up your survey with good survey geometry, made sure the geophones are well coupled to the ground. The field techniques make a big difference with your data. The processing really is just the final polish. We'll hit OK. This is going to take some time, so I'm going to speed up the video. And our inversion has completed. We'll hit OK. This is now our new velocity model here. And you can see it created this zone here, but this is what we got. And then we'll go to dispersion 1, and now we can see our new RMSE errors. Now, the last thing you would do with this data is you would save it as an RST file here, and you just save it as higher mode example to RST. You can just hit save there. And that is how you would process atom seismograph data that collected a higher mode, and the best way to process that, the different techniques you would need. Thank you for watching.